This short training will help you understand calibration of the ABI in general and impacts of the faulty loop heat pipe on GOES-17 in particular. I'm Scott Lindstrom from SIMS. I've produced this training with input and guidance from many, especially from Tim Schmidt. Others are noted here. This figure shows mirrors that redirect infrared energy to the detectors on ABI. And it also shows how cold the detectors are designed to be operated at, 60 Kelvin. That cold temperature means very little energy at the wavelength being sensed is being emitted by the mirrors. In reality, the temperatures are warmer, and even more worrisome for overnight hours during certain times of the year. The temperature changes with time, so calibration values are inaccurate. These are the different parts of the ABI. The IR Cal target is the internal calibration target that is used frequently to determine the hot end of the calibration scale. The calibration look takes into account any radiation that is coming from the satellite, presumed to be at a steady temperature. However, as the focal plane temperatures increase at night, when the ABI is illuminated by the sun at certain times of the year, calibration values aren't accurate. Here's a picture of the back part of the ABI assembly. You'll see a more complete image next. The yellow tubes, they're very thin, are the loop heat pipe. They are designed to move heat from the interior of the satellite, near the sensor, to the radiator on the outside of the ABI. Because they do not function as designed in GOES-17, too much heat builds up within the ABI on GOES-17. Here we have a more complete cartoon of the ABI. The yellow pipes of the loop heat pipe mechanism are still there. You can infer from this image that the loop heat pipe removes heat from the interior of the ABI. The parts on the right, the control electronics and the electronics unit, are separate from the ABI. For more complete details, see the GOES-R data book. This figure shows the change in temperature for the focal plane within the GOES-17 ABI. The temperature is fairly steady for much of the day around 82 Kelvin, and then as the sun illuminates and heats the satellite, temperatures start to warm. Note that the change is approximately linear. Thus, the calibration can be approximated by extrapolating forward in time based on the calibration at the present time and the one at the previous time. This reduces the bias in the calibrated values to acceptable values. At some point, the satellite becomes so warm that the amount of energy being detected saturates the sensor. At worst, this means more than 6 hours of unusable data. That exact amount of time for which no data can be used varies by band and by date. Predictive calibration allows for better calibration of the usable data, but when saturation occurs, data are lost. Those data are lost even when predictive calibration is used. This chart shows a prediction versus the observation on the previous slide for one day of the peak temperature of the focal plane through the course of the year. Note how eclipse season rescues the satellite for several weeks around the equinoxes when the solar forcing would otherwise be most detrimental. The effects of perihelion in January and aphelion in July are also apparent. Approximate temperatures when the sensor saturates for a given wavelength are also indicated. The number of days when a band is impacted is different for different bands. This figure shows the difference between GOES-16 and GOES-17 values in the mean for a 401 by 1001 scene on the equator equidistant between the two satellite subpoints. As the satellite warms up, and this is shown for just about the worst day, starting around 9Z, GOES-17 brightness temperatures start showing a warm bias. That ramp up in temperature is when Predictive Cal will be used to give values that are more accurate. There is still a data gap when everything saturates. As the satellite cools off after saturation, there is a cool bias. Predictive Cal will make values here more accurate as well. But note that there will be significant times, almost 6 hours on the warmest day, when no data are present. This animation shows both stray light mitigation early in the evening, and then the effects of the loop heat pipe for 15 April 2019. One of the days when the solar forcing of the ABI is strongest. Infrared channels on GOES-R satellites are calibrated after a space look. Space is inferred to have a temperature of around 4 Kelvin, and a look at the internal calibration target, ICT, with a temperature around 300 Kelvin, These are used to anchor the cold and warm ends of the scene. When the satellite detects energy coming from the Earth atmosphere system, then, it can determine where that observation falls in the range between the space look and the ICT look. This all assumes a steady state and temperature of the satellite. A time chart for GOES-17 shows when space looks and the ICT looks occur. These are more frequent ICT looks for GOES-17 compared to GOES-16, which has only one each 10 minutes. This is an attempt to give more accurate calibration for a sensor that is not a constant temperature. This plot shows maxima in blue, mean in black, and minima in cyan values for the gain on GOES-16. Think of the gain as the inverse of the slope between the space look and the ICT look. It's a good thing that values do not change. That means that the on-orbit calibration is accounting for any contamination in measurements caused by radiation emitted by the satellite, for example, and an accurate, well-calibrated value can be deduced. When the loop heat pipe isn't working right, the entire satellite will become progressively warmer as the sun illuminates the ABI. As it warms, the ABI emits more radiation, and the observation of Earth-emitted radiation will be contaminated by that increase in radiation from the satellite, more than is calibrated for. As the focal plane temperature increases, there will be a warm bias to the observed brightness temperatures. This image shows gain changes for the 10 infrared bands on ABI. This chart is for the worst day, April 15th, when the warming of the ABI is most severe. After the satellite has warmed and reached a peak and starts to cool, the calibration will be typically for a warmer temperature than is observed. Thus, less radiation is detected than is calibrated for. That is, the amount of radiation at the wavelengths being detected will be less when the observation is taken than when the calibration value is defined. This leads to a cold bias. If you use predictive calibration, shown here in the center image, the comparison with GOES-16, here over CONUS midway between the two subsatellite points, a region chosen to mitigate view angle differences, you have cloud top values more in line with what is viewed by GOES-16. Compare the brightness temperatures in the cold clouds over the Sumter Rockies. They are too warm with GOES-17's original calibration, contaminated as it is by a steadily warming satellite. The warm region over northwest Mexico is also more consistent with GOES-16 in the predictive calibration image. After the peak in lack of cooling by the loop heat pipe on GOES-17, there's a period when the original calibration, shown here on the left, will be too cold compared to the GOES-16 in the same region midway between the two satellite subpoints. Cold cloud tops over northwest Wyoming and in Idaho, for example, are cooler with the original calibration, but they're more in line with GOES-16 values with predictive calibration in the middle image. Here are some final thoughts on predictive calibration scheduled to be implemented in summer of 2019 and the loop heat pipe problem on GOES-17. Thanks for listening.